All right, continuing our pre-calculus exam review, we're going to be focusing on sketching rational and polynomial functions. In this lesson, again, there'll be some extra content. We'll have to talk a bit about finding the roots of polynomials as well. It's all in there, so like I had mentioned before, work through these problems with me in preparation for your upcoming exams. For the other parts of this lesson, see the linked lessons at the end of this video or see the playlist titled Pre-Calculus Exam. All right, so starting us off here, we're going to look at graphing the following functions here. So taking a look at our first problem here, we have a rational function. This is defined to be 8x plus 6 divided by 4 minus 2x. So the idea with graphing rational functions is we want to find all the characteristics of this rational function. That includes our x-intercept, y-intercept, vertical asymptotes, horizontal asymptotes if they exist, etc. So taking a look here, we first find our x-intercept. X-intercept exists when the numerator is 0. So in this case here, we're going to have 8x plus 6 equaling 0, which implies x is negative 6 over 8. Reducing that, we have an x-intercept dividing top and bottom by 2 of negative 3 over 4. So we have an x-intercept of minus 3 over 4. There's one of our roots. Y-intercept happens when you evaluate the function itself at 0. Evaluating the function itself at 0 here, you'll see we end up getting 6 over 4, and reduce that becomes 3/2. Continuing on here, you'll notice that the degree of the top and the degree of the bottom are the same. Whenever the degree of the top and bottom are the same, we create what's called a horizontal asymptote. So we have a horizontal asymptote here. The horizontal asymptote is going to be y equals to, it's the division of the leading coefficients of the top and bottom. Leading coefficient of the top is 8. Leading coefficient of the bottom is negative 2. So dividing out that 8 and the negative 2, we end up getting negative 4 here for our horizontal asymptote. So we now have our x-intercept at negative 3/4, y-intercept at 3/2, a horizontal asymptote at y equals negative 4. Vertical asymptotes exist when the bottom is 0. The bottom is 0 when 4 minus 2x equals 0, or in other words, x is equal to 2. Now that we have all the characteristics of our rational function, let's go ahead and graph. All right, if we take a look here, here is the graph of f at x. Here you'll see that I've got my horizontal asymptote at negative 4, a vertical asymptote at 2. And you'll notice here we've got our x and y intercepts that we had identified. To get this graph here, you'll notice as I approach 2 from the left-hand side, what's going to happen here is that these values here and the top will be positive. The values on the bottom here will also be positive, and therefore positive divided by positive is positive. So that means as we approach 2 from the left-hand side, we'll be approaching positive infinity. Now my function must then approach my horizontal asymptote, so it has to go down here, and you're approaching your horizontal asymptote at negative 4. On the other side of the vertical asymptote, as I approach 2 from the right-hand side, we're picking numbers slightly larger than 2, so let's say 2.01. And what you're going to find here is the top will be positive again, but the bottom this time will be negative. Therefore, we're below the x-axis. So the graph has to look something along these lines. So the graph must then be approaching negative infinity as we get closer and closer to 2 from the right-hand side, and then tend up towards its horizontal asymptote at y equals negative 4. Let's take a look at another rational function. All right, taking a look at the next graph here, they want us to graph the following rational function. This is f at x is x plus 3 over x squared plus 4x minus 5. Once again, let's go ahead and find all our characteristics of this function. The x-intercept happens when the top is 0. The top is going to be 0 at x equals negative 3. It's always a good idea to fully factor your rational function just in case there's any holes in the graph here. We don't have any. So we do have our x-intercept at minus 3. Your y-intercept happens when you evaluate the function at 0. Evaluating the function at 0, we get negative 3/5. Vertical asymptotes exist when the bottom is 0. Setting the bottom equal to 0, we have x equals negative 5 and 1. You'll notice here the degree of the bottom is 2 and the degree of the top is 1. Whenever that happens, we now have a horizontal asymptote at y equals 0. And now we can go ahead and graph our rational function. All right, graphing our rational function, we have the following. You'll notice here, as I approach 1 from the right-hand side, picking numbers slightly larger than 1, like 1.01, we're going to end up getting positive, positive, positive. That means that as I approach 1 from the right-hand side and I approach my vertical asymptote, this ends up going to positive infinity. Then it will tend towards my horizontal asymptote at 0. On the other side of the graph, the extreme other side, as I approach negative 5 from the left-hand side, summing in numbers slightly less than negative 5, let's say negative 5.01. Summing that in, we're going to get negative, negative, and negative. 3 negatives results in a negative value, so we're below the x-axis here, and therefore our graph has this shape to it. And then in between this here, I have my x-intercept and my y-intercept here. As I approach negative 5 from the right-hand side, picking numbers slightly larger, like negative 4.999, we're going to get negative, positive, and negative, which is going to be above the x-axis, positive value, so we're tending towards this way. Then we go down, cross our x-intercept, our y-intercept, and then tend towards negative infinity as we approach 1 from the left-hand side. And here is our graph of the following rational function. All right, in the next example here, we have the following rational function, x squared minus 5x plus 4 over x squared plus 2x minus 15. Step number 1 for this is going to be fully factor the top and bottom. So fully factoring the top and bottom, we get x minus 4 times x minus 1 on the top and x plus 5 times x minus 3 on the bottom. Going ahead and finding our x-intercepts, I get x-intercepts at 4 and 1. Your y-intercept happens when you evaluate the actual function at 0, in which case we get negative 4 over 15. Vertical asymptotes exist when the bottom is 0. We're going to have 2 of them at negative 5 and 3. And you'll notice here right away the degree of the top and bottom are both equal. They're both equal to 2. So we have a horizontal asymptote, and that's going to be the division of the leading coefficient of the top and bottom, which are both 1. So you end up getting a horizontal asymptote at 1. Let's go ahead and graph this and take a look. All right, going ahead and graphing this, we get the following. You'll notice here I have my horizontal asymptote at 1, vertical asymptotes at negative 5 and 3. I've got my y-intercept happening below the x-axis, my root here at 1, and then another root at 4. Again, to find out these values here, the only thing you have to do is go ahead and sub in some numbers, and you can kind of see where everything's at here. So picking numbers to the right of 3, let's say 3.01, 3.001, etc. As I approach 3 from the right-hand side, we can go ahead and sub that into this expression to see whether it's positive or negative. Subbing this in here, I get a negative value, a positive value, a positive value, and a positive value. So the result is negative. So that means that as I approach my vertical asymptote from the right-hand side, I'm coming from below. That'll tend up to my root and then go towards your horizontal asymptote. Again, picking a number as I approach 3 from the left-hand side, you'll find it's positive, so I was coming from above. And I had to cross, you have to cross your horizontal, and keep in mind that your horizontal asymptote exists when you let x get to positive or negative infinity. So as x approaches positive or negative infinity, that's how your horizontal asymptote is created. So locally, you can cross your horizontal asymptote. It's just the outer bounds of the function. As x gets infinitely large or infinitely small, does your function approach a horizontal asymptote. So horizontal asymptotes can be crossed, unlike your vertical asymptotes, which can never be crossed. So at any rate here, as I tend towards my root, I then cross my y-intercept, and then it would go back down. Now I know that it was not going to jump back up here because I would have needed a second root for that to happen. So the only possibility is as I tend towards negative 5 from the right, I must be tending towards negative infinity. And likewise, if you pick a number to the left of negative 5, let's say negative 5.01, we would have found that this would have been negative, 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 and those 4 negatives would have been positive, so I know I was above the x-axis going this way, and then you would tend towards your horizontal. All right, let's continue our exam review. All right, taking a look at our next examples here, we're going to be taking a look at division. So here we have our polynomial here, and we're dividing this by x plus 3. So whenever you are dividing by a linear divisor, you have a couple of options. One is using synthetic division. Let's go ahead and break this up. Just as a reminder, your division algorithm says the following. Your polynomial, in case this is your p at x, will break up into its quotient times divisor plus remainder. So doing synthetic division here, we get the following. So you'll notice here doing synthetic division, you evaluate the root, which is minus 3. I then copy the coefficients down, so 2, negative 9. There is no x squared, so I had to put that 0 in, and then the 2 and the 8. Going through synthetic division, we have the following decomposition. This value at the end always represents your remainder, and this represents my quotient, 1 degree less. So therefore my polynomial, p at x, that's this polynomial here, must break up into the quotient. We start off with degree 4. This is now degree 3, so this will be 2x cubed minus 15x squared plus 45x minus 133 times the divisor, and then plus your remainder. So the quickest way is going through synthetic division, and you can break down your polynomial this way, and then using your division algorithm, you now divided this out. Let's take a look at the next question. So in this problem here, same sort of idea, except for we're dividing by a nonlinear factor. When that's the case, you have to actually go through a long division process. So our long division process says this is my divisor, and this is my polynomial. So we're going to go ahead and divide this out here. Going through the process here, we get the following. I end up getting a remainder of this question of 2x plus 27. This represents our quotient, and this represents our divisor. So our polynomial, this is our 8x to the fourth plus x cubed minus 3x squared plus 1. That's going to go ahead and equal our quotient times divisor plus our remainder. And now we've divided out the following expression. All right, let's continue our exam review. So in the next examples here, we're going to ask to list all the zeros of the following polynomials and the idea of their multiplicities, associated multiplicities. So let's go ahead and find these roots here. So they give us this third degree polynomial. I'm going to have to factor this. So whenever you're factoring, looking for roots, first thing you look for is a GCF. This has a GCF of x. Inside it'll leave me with 4x squared plus x minus 3. Now if I take a look at this polynomial here, this quadratic, I can go ahead and calculate the discriminant of this. The discriminant here is going to be my b squared, which is 1, minus 4 times your a value, which is also 4, and your c value is negative 3. This ends up equating to being 1 plus 48, and I get my discriminant here is 49. So my discriminant here is a perfect square. This will factor nicely if you take a look here. And quickly using charting, I see this factors into 4x minus 3 times x plus 1. So for this question here, we have the roots or zeros of this degree 3 polynomial are such that we have a 0 at 0, and the multiplicity on that is 1. I have another 0 at 3/4, also with a multiplicity of 1, and then my last 0 at minus 1 with a multiplicity of 1. And to remind you, the idea is that if you add up your multiplicities, that'll end up adding up to the degree of your polynomial. So this is a third degree polynomial. I was looking for 3 roots up to multiplicity. It turned out that all 3 of those roots were real. All right, let's take a look at another example. So in the next example here, they actually gave us a degree 5 polynomial, but they had fully factored this for us. If you take a look, this is now fully factored, and they want us to identify the zeros and multiplicities. And you'll see here, this has a root of 1, and we'll call that a multiplicity of 2. This will generate a root at negative 8 with a multiplicity of 1. And lastly, this will generate a root at 2 with a multiplicity of 2. So again, adding up those multiplicities, it should come out to the degree of the polynomial. You'll notice this is 2 plus 1 plus 2 is 5, and that's the degree of our 5th degree polynomial here. Let's take a look at some more examples. We have to break down the polynomials ourselves. All right, in the next example here, we want to find all the zeros of the following polynomials. So they give us this third degree polynomial here. X cubed plus 10x squared plus 29x plus 20. And when you want to factor and find zeros, the first thing you want to do is look for a GCF. If I take a look here, there's not a GCF on this. I don't have an x I can factor out of here. There's not a common constant, you'll notice here, of the 20 and the 29. So in that situation, we have to use synthetic division to find a root. You're going to want to apply your rational root test here to give you a complete list of possible rational roots that the polynomial may have. Using the rational root test, we get the following. So using the rational root test here, again, your c value is a complete list of factors of your constant term, and your d value is a complete list of factors of your leading coefficient, which is 1. Then you take your c over d, and that gives you a complete combination here. You'll notice because the d value is plus or minus 1, we just ended up essentially just getting our c value. Now this gives us 1, 2, 3, 4, 5, 6. This gives us 12 different combinations to try out to find if one of these is a rational root. You'll make the quick observation here that we're summing all of these values, and we're adding, like this is a positive 20 at the end. So we know that if I sub in any positive number here, there's no way that that's going to go to 0. So therefore, we can reduce the list to just be the negative values. So the possible rational roots are -1, -2, -4, -5, -10, and -20. So let's go ahead and try synthetic division on the -1. And right away, trying synthetic division on the -1, I end up getting here a root at -1. We know this is my quotient, so therefore our polynomial f at x will factor into x plus 1 times x squared plus 9x plus 20. And then we have a simple trinomial here, and this becomes x plus 1, and this factors into x plus 5 times x plus 4. So you can see here this polynomial has roots at -1, -4, and -5. Let's take a look at another. So in the next example here, we want to go ahead and factor this. So taking a look here, once again, I don't have a GCF I can factor out. Looking for factor by grouping, I'm not seeing that working either because we have an odd number of terms. So I'm going to go ahead and do synthetic division again. Let's do the rational root test here once again, which gives us the following. Go ahead and doing the rational root test, I end up getting the following values here. Because of the pluses and minuses, I can't, as in the first example, get rid of all the positive numbers or negative numbers. We can't do that, so you have to look through all of these. So I'm going to go ahead and start synthetic division, starting with a 1. So you'll notice here, I tried it at 1, did not work. I tried it at -1, it did work. So this has a root at -1, and this will be our quotient left over. So my polynomial f at x will factor as follows. All right, so now I'm left with x plus 1 times x cubed minus 4x squared minus 3x plus 18. You'll notice right here, now we have to factor this up, but again, there's no GCF on this. Factor by grouping will not work, so we have to continue with our synthetic division. If I'm going to continue synthetic division, the same list that we created up here still applies to our smaller sort of factored polynomial. One thing to be aware of is we should try -1 again, because we could have a double root at -1. So I'm going to go ahead and do synthetic division now using this polynomial and using this list up here again. We've already tried 1 and we know it doesn't work. -1 did work for the larger original polynomial. I want to try it again to make sure that it's not a double root here. And then we'll continue on to 2, -2, etc. All right, going through synthetic division again here, I tried the -1, the 2, the -3. At the 3 here, it worked out, and I've got my quotient here. So going ahead and doing this, now I know my polynomial f at x breaks up as follows. And you'll see here we get the x plus 1 from before, x minus 3, and then we get a quadratic here. This will factor quite easily, giving us the following. And you'll see our polynomial f at x factors into x plus 1, x minus 3, quantity squared, times x plus 2. You actually see here when I started doing synthetic division, I forgot to check the -2. I did the 2 and I went right to the -3. I would have found the root of -2 first. But at any rate, I found the other one later on. That was at 3 here, as you see. So our polynomial factors as follows. So again, this has a roots at -1 with a multiplicity of 1, 3 with a multiplicity of 2, and -2 with a multiplicity of 1. All right, let's take a look at another example. So in the next example here, we have a degree 4 polynomial. And you'll look again for GCF. We do not have it. We'll take a look for factor by grouping, also not working. So we're going to go again right to the rational root test. This time you'll notice the leading coefficient is not 1 here. Doing the rational root test, we get the following. Again, doing the rational root test here, I first calculated my C value is factors of -2, and my D value is factors of 9 here. And then I went ahead and did all combinations for those, and now we have our complete list of possible rational roots this polynomial has. Again, because of the pluses and minuses here, I can't eliminate either all the positive or negative ones, so I'm going to go right to synthetic division. Going ahead and doing synthetic division here, I get a root at 1, and our polynomial factors as follows. I now want to continue factoring here. You'll notice here now I want to factor this degree 3 polynomial. We're still using the same list of rational roots we created, but you'll notice that we're all adding all these terms together here. Therefore, none of the positive values can be roots, so I can go ahead and reduce my list of rational roots to the following. All right, let's go ahead and do synthetic division on these values. And going through synthetic division here, you'll see I tried the -1, it did not work. The minus a third, it did not work. The minus a ninth. And I did have some luck at the minus 2 here. It became a root. So now my polynomial, h at x, will factor as follows. X times 1 times x plus 2 times this quadratic here. The following quadratic is a perfect square, and our final answer is h at x is x times 1 times x plus 2 times 3x plus 1 quantity squared. And we get our fully factored polynomial. This has roots at 1 with a multiplicity of 1, minus 2 with a multiplicity of 1, and minus a third with a multiplicity of 2. Again, as a reminder, when you add up those multiplicities, you get the degree of the polynomial itself, which in this case was 4. Let's take a look at some more examples. All right, in the next examples here, we want to sketch the following polynomials. So after working on your factoring, and in this case here, we now have this fully factored, we can go ahead and sketch the polynomial. To sketch the polynomial, draw yourself a number line. Identify the roots here. We have a roots at -5, another root at 1, another root at 3. And then what we want to do is pick a number within each interval. So now I'm going to pick a number greater than 3. Let's say I pick 10. If I sub a 10 into here, we're going to get positive, positive, and positive. And don't forget, we're multiplying by that minus sign in the front, so the resulting value will be negative. That means we're below, and we're coming from somewhere down here. And the idea here is that you're going to tend towards your root, and if the multiplicity on the root is odd, you're going to cross, and then it'll tend back towards your root. If the multiplicity on that root is odd, you're going to cross, and then I'm going to tend back up towards the root, and if the multiplicity on that root is odd, we're going to cross. So the general shape will look something like this. The multiplicities here are all odd. You'll notice this has a root of 1, 3, and minus 5, each with a multiplicity of 1. So the general shape of our polynomial function will look something like this. All right, let's take a look at another. The next example here, again, this is fully factored for us. Once it's fully factored, identify your roots. My roots here are at -6, -4, and -2. Now pick a number greater than -2. Again, let's say we pick a 10. That's going to be positive, positive, and positive. That means we're coming from above here. As I tend towards my root here, you'll notice at the -2, we have a multiplicity that is even, so we're going to bounce off that root. At the -4, it's going to be a cross, and at the -6, it's also going to cross. So the general shape of this higher order polynomial will be something along these lines here, where we are bouncing off of that root. Again, that multiplicity was even, it's a 2, so we're going to bounce off that root, tend towards our next root, we're going to cross because it's odd, tend back up towards the root of -6, cross because it's odd, and we have our polynomial. All right, that concludes this segment of our pre-calculus exam review. Thank you.